Hi my dear students, welcome back to our amazing YouTube channel of Brilliant Katha. This is the second lecture in JEE Mantra Series, and in this lecture we will be revising the topics sets, relations and functions. Okay, now we'll start with sets first. Set is a well-defined collection. Set is a well-defined collection. It's not just a collection of elements, friends. It is a well-defined collection of elements. Okay, now once we define set, then we should know how to represent a set. Sets can be represented in two different forms. One is roster form, another is set builder form. In roster form, we list out all the elements, whereas in set builder form, we won't list out the elements. We just write its property possessed by the elements. Example, let set A is equals to set of 5 elements 1, 2, 3, 4, 5. This way of representing the set is called as roster form. In roster form, all the elements are listed and 2 elements are separated by comma and set is enclosed in curly brackets. Next, the same set in set builder form, we can write it as set A is equals to, we take a particular variable x, set A is equals to set of all variables x such that, now we define what is this x. X should be a natural number and x less than or equals to 5. So if I say x belongs to capital N and x less than or equals to 5, that means x can take 1, 2, 3, 4, 5. That is nothing but the same set. So we can represent the same set in two different forms. One is roster form or we say set builder form. Next, different forms, different types of sets we see, starting with null set. A set without any element, a set which consists no element. Generally, a set which consists no element looks like this. Empty set we say, or null set we say, void set. We can also represent null set as 5. Either empty curly brackets or 5. This particular set we call it as null set or void set or empty set. Next, singleton set. A set consisting only one element. Set A is equals to set of 1 or like set of 5. Such sets are called as singleton set. That means this set is consisting only one element. Next, finite set. A set consisting finite number of elements. If I say set of natural numbers, is set of natural numbers a finite set? No. It starts with 1, 2, 3 and so on. There won't be finite number of elements in the set. So finite set means a set consisting finite number of elements. Set A is equals to set of prime numbers less than 10. Set of prime numbers less than 10. So 2, 3, 5, 7, that's it. 2, 3, 5, 7 are the prime numbers which are less than 10. Next, equal sets, equivalent sets. Two sets capital A and capital B are said to be equal sets. Two sets capital A and capital B are said to be equal sets if all the elements in A are also in set B and all the elements in B are also in set A. Then we call it as two sets capital A and capital B are said to be equal sets. Equal sets means, I repeat, all the elements of set A are in set B and all the elements in set B are in set A. Then we call two sets capital A and capital B are two equal sets and we write them as A is equals to B, friends. We write A equals to B. I mean to say, suppose set A is equals to some 2, 3, 4. Even if set B is also equals to, now look at, there are 3 elements in set A, 3 elements in set B. And elements in set A are 2, 3, 4, whereas in elements in B are 3, 4, 2. Forget about the order of the elements they occurred, but we have the same element. 2 is an element of A, 2 is an element of B, 3 is an element of A and B, 4 is also an element of A and B, and no other element in B is extra as compared to set A. In the same, no other element in A is in B. So these two sets capital A and capital B are said to be equal sets. If two sets are equal, we write it as A equals to B. Next, equivalent sets. Equivalent sets means it's not about same elements. It's only same number of elements. If capital A and capital B are having same number of elements, suppose 4 elements in set A, 4 elements in set B, then we call such two sets are called equivalent sets. Say set A is equals to 4, 5, 6, 7. Set B is equals to A, B, C, D. Set A 4, 5, 6, 7. Set B, A, B, C, D. Now if we compare, these two sets are not equal, but they have same number of elements. 4 elements in set A, 4 elements in set B. So we call it as equivalent sets. Capital A comma B are called as equivalent sets. Two equal sets are always equivalent sets. Clear? Next, order of a finite set or cardinal number. The number of elements of a set, the number of elements of a finite set is called its order, or we say cardinal number. Let's say set A is equals to 1, 2, 3, 7, 8, 9. Then n of A denotes the number of elements in a particular set. N of A denotes the number of elements in a particular set, and n of A is equals to 1, 2, 3, 4, 5, 6. There exist 6 elements in this particular set. Number of elements in a set is called its order, or we say cardinal number. This is defined only for finite set, because for infinite set n of A will be infinite. Next, different types of sets. As we have seen already, subset, superset. If all the elements of A are also the elements of B, if all the elements of A are also the elements of B, then we call it as A is subset of B. If all the elements of A are also the elements of B, then we call A is subset of B. If A is subset of B, implies B is superset of A. B is superset of A. If A is subset of B, then we call it as B is superset of A. This is how we denote subset. And this is how we denote superset. Next, proper subset. Proper subset means all the elements of A should also be the elements of B. That means A is subset of B. And if A is not equals to B, A is subset of B and A is not equals to B, then we call A as a proper subset of B. A is called as proper subset of B. Clear, friends? Are you getting me? See, A is subset of B means all the elements of A are the elements of B. That's it. If all the elements of A are also the elements of B, then we call A is subset of B. If A is subset of B, then B is superset of A. Next, coming to proper subset, A should be subset of B, and if A is not equals to B, then we say A is proper subset. This is how we denote proper subset. This is how we denote proper subset. So if A is proper subset of B, that means A can be subset of B and A shouldn't be equals to B. Next, let's see, for a given set, what are all the subsets? Suppose set A is equals to some set of 1, 2, 3. Empty set is a subset of every set, friends. Empty set will be a subset of every set. So empty set is subset of A. Next, set of 1, set of 2, set of 3, set of 4, set of 1 comma 2, set of 1 comma 3, set of 2 comma 3, and every set is subset of itself. Set of 1 comma 2 comma 3. So total number of subsets for a given set are 1, 2, 3, 4, 5, 6, 7, 8. So if a set having 3 elements, it has 8 subsets. So we have a formula: if number of elements in A is equals to n, if there are n elements in set A, then total number of subsets is 2 power n, friends. 2 power n. If a set consisting n elements in it, then it has 2 power n subsets. And one more thing, Of these 2 power n, if I say number of proper subsets, proper subsets means this will be a proper subset of A, this, except itself. Okay, so that particular 1, 2, 3 will be excluded among all the subsets, because we are discussing about only proper subsets. So total number of proper subsets of a set A consisting n elements means we'll just exclude only itself. That means total 2 power n minus 1. Next, number of non-empty subsets. Is also equals to 2 power n minus 1, because we exclude this empty set. Clear? So we have seen subset, superset, proper subset, and number of subsets, number of proper subsets, number of non-empty subsets for a given set consisting n elements in it. For a given set consisting n elements in it, we have seen total number of subsets, proper subsets and all. Next, power set, universal set. Power set means if capital A denotes any set, friends, if capital A is any finite set, then the set of all the subsets of capital A, is called as power set of A. That means if set A is 1, 2, 3, same set we take, what are all the subsets that we have for this empty set? Set 1, set 2, set 3, set 1, 2, set 1, 3, set 1, 2, 3, and last set 1, 2, 3. Now, if there is a set which is consisting all these subsets as the elements of that set, then such a set is called as power set of the given set. So if capital A is any set, its power set is denoted as P of A. P of A denotes its power set, friends. P of capital A means power set of A, which is nothing but including all the subsets of the given set. In the elements of P of A, what are all the elements of P of A? All the subsets of capital A. Next, as we have seen, number of subsets of A, if A has n number of elements is 2 power n. Just now we have seen, if n of A is equals to n, then number of subsets of capital A is equals to 2 power n we have seen. So that means for a set consisting n elements, 2 power n subsets. Now in P of A, all these 2 power n subsets will be as elements, no? So what will be n of P of A? That means number of elements in P of A will be 2 power n only, because all these subsets will be the elements of P of A. So n of P of A is equals to 2 power n. Next, universal set. Universal set is something, friends, where a set consists all the elements under consideration. All the elements under consideration means, suppose if I say set A, if I take 1, 2, 3, set B if I take 4, 5, 6, some set C if I take, I have defined 3 sets, 5, 6, 7, set D, set anything. Now if there is a set which is consisting all these elements, first thing, all these elements, then such a set is called as universal set. Okay? Every set should be a subset of universal set. Every set is a subset of universal set. So in general we denote universal set with capital U like this, and universal set in this context it will be 1, 2, 3, 4, 5, 6, 7. So these elements should be must. These elements should be must. Apart from this, 8, 9, 10, anything and all. Because every set should be subset of universal set. Or we say universal set is superset of every set. Universal set is superset of every set. So in simple words, we define universal set as the set consisting all the elements under consideration. Under consideration. That means under a particular context, If a set consisting all the elements related to that context, then such set is called as universal set. Next, operations on sets. We have some good number of operations with respect to sets. They are union, intersection, difference, symmetric difference, complement. First we start with, for a particular set, let's say set A is equals to 1, 2, 3, 4 and set B is equals to 3, 4, 5, 6. Let A comma B are any two finite sets, friends. Then union of two sets. Union of A comma B is A, we denote it as A union B. We generally read it as A or B. A union B, or we say A or B. This is nothing but X such that X belongs to A or X belongs to B. A union B is nothing but X such that X belongs to A or X belongs to B. So under this context, A union B is X belongs to A or X belongs to B or both. So that means 1, 2, 3, 4, 5, 6 is our A union B. Next, intersection. We denote intersection like reverse U. It is of the form reverse U. And it is defined as X such that X belongs to A and, friends, intersection means and X belongs to B. So in this context, intersection means the common elements in both, friends. That is 3, 4. Next, third one, difference. Suppose if I say A minus B, I mean to say X such that X belongs to A and X does not belongs to B, friends. X belongs to A and X does not belongs to B. So X belongs to only A, we say. Only A means only 1, 2. In the same way, B minus A means elements which belong to only B. Only B except A. Next, symmetric difference. Symmetric difference is simple words. Symmetric difference is denoted as A delta B, friends. Symmetric difference means A delta B, and A delta B is equals to A minus B union B minus A. A minus B union B minus A, or we can even say this as A union B minus A intersection B. All this comes under symmetric difference only. So from 1, 2, 3, 4, 5, 6, we just exclude 3, 4. So in this context, it is 1, 2, 5, 6 will be the symmetric difference. Next, complement. Whenever you say complement, we always stick to universal set. Suppose let's say universal set capital U is defined as some 1, 2, 3, 4, 5, 6, 7, 8. Let's say U is all the set of natural numbers from 1 to 8. Now, A complement of A is denoted as like this, friends. This is nothing but X such that X does not belongs to A. X does not belongs to capital A. Does not belongs to A means all the elements except A. All the elements of universal set except A. So that becomes in this context as X as A is 1, 2, 3, 4. So except 1, 2, 3, 4 we have 5, 6, 7, 8. From universal set we just exclude 1, 2, 3, 4, friends. So whatever the thing that we got, that is said to be its complement. A complement. Generally we call A complement as mu minus A. Universal set minus that. And A complement whole complement is set A itself. Next, Venn diagram. Venn diagram means the pictorial representation of a set, friends. The pictorial representation. The pictorial representation. In general, pictorial representation, a universal set is taken as some rectangle and all the sets which are subsets of it, let's say capital A, capital B, all these sets are just some circles, some closed shapes, anything. Now in previous case what we have, friends? In previous case we have taken elements set A 1, 2, 3, 4, set B 3, 4, 5, 6, and in universal set we have from 1 to 8, no? So 1, 2, 3, 4, 5, 6, 7, 8. Let's try to plot these on the by using Venn diagram. Let this be set A, this be set E, U. This is the region common to both. So this region is called as A intersection B. Now what are the elements in common to both? 3, 4. Now in set A we have 1, 2, 3, 4. So already 3, 4 are here, 1, 2 will be here. In set B 3, 4, 5, 6. Already 3, 4 are here. So 5, 6 will be here. Now this two elements 7, 8 neither in A nor in B. So they will be somewhere outside of A comma B, outside of A comma B and inside U. So this is how we represent a set in terms of Venn diagram. Venn diagram means this is pictorial representation of sets, friends. By using this we can easily say what is A union B, A intersection B, A minus B, B minus A union B whole complement, A intersection B whole complement. All these things can easily be explained by using Venn diagram. Next, Venn diagram. After Venn diagram, we have laws of algebra of sets. Different laws of algebras. Commutative law. We know A union B is equals to B union A, as well as A intersection B is equals to B intersection A. Commutative law we say. Associative law of sets. A union of B union C is equals to A union B union C, or even in terms of intersection, A intersection of B intersection C is equals to A intersection B whole intersection C. Distributive law. A union of B intersection C is equals to distribution, friends. A union B intersection A union C. In the same way, A intersection of B union C is A intersection B union A intersection C. These are the different laws we have. Next, De Morgan's laws. These De Morgan's laws are very important. A union B whole complement is equals to A complement intersection B complement, and A intersection B whole complement is equals to A complement union B complement. We just change this. If it is intersection, we'll change it to union. If it is union, we change it to intersection. Next, identity laws. A intersection universal set. You know universal set, na? A intersection universal set is the given set itself, na? And A union null set is the same set itself. These laws are called as identity laws. So these are the different laws of algebra of sets. Next, important results on cardinal number of sets. Cardinal number. Generally for two sets, friends, we start with first. Number one, for two sets. Capital A comma B. In that the first one is number of elements present in at least one set. Number of elements present in at least one set is denoted as n of A union B, friends. And n of A union B is equals to n of A plus n of B minus n of A intersection B. Next, number of elements present in exactly one set. In exactly one set, we write this as n of A plus n of B minus twice n of A intersection B. Number of elements present in exactly one set. This we use in sets, this we use in permutation combination, this we use in probability also. The principle of inclusion and exclusion from permutations and combinations we derived from this only. We got it from this. Next, for three sets, capital A comma B comma C. Actually, this is very important. Majority of the times we come across this. So for three sets, number of elements present in at least one set. If I say at least means union, friends. Number of elements present in at least one set will be n of A plus n of B plus n of C minus n of A intersection B minus n of B intersection C minus n of A intersection C plus n of A intersection B intersection C. We also have number of elements exactly in one set, exactly in two sets also in this, but once you know this, then we'll get everything. These three are the most important from cardinal number results, cardinal theorem results. Next, so with that we are done with the sets, friends. Now we are entering into relations. First, ordered pair. Two elements, a pair of elements enclosed in parenthesis, enclosed in open brackets, represented or given in a particular order, we call it as ordered pair. The best example of ordered pair is, how do we represent a point in the Cartesian plane? Every point in the Cartesian plane is represented as an ordered pair of two coordinates, x coordinate comma y coordinate. Can we interchange x and y? No. So x should be always in the first position, y always should be in the second position. That's the reason we call it as ordered pair. So a pair of elements like say A comma B is an ordered pair only when we say like A should be the first element and B is second element. You can't write A comma B as B comma A, okay? Because in B comma A, B is first element, A is second element. So A comma B is not equals to B comma A. Now next, unordered pair. Unordered pair means just a pair of elements, not in any order. A pair of elements without any particular order is called it as unordered pair. In unordered pair, A comma B is equals to B comma A. Whereas in ordered pair, A comma B should never be equals to B comma A. Clear? This is different. This is one case and this is one case. Like 1 comma 2 is a point. 2 comma 1 will be another point in the Cartesian plane. These two won't be the same points. Whereas unordered pair means just a pair of elements. That's it. A pair of elements. I say selecting two numbers out of 10 numbers. Whether you say 1 comma 2 or 2 comma 1. It's only selection matters. So it's not the order of selection. Clear? Next, Cartesian product of two sets. Let set A is consisting 3 elements 1, 2, 3. Set B consisting 2 elements A comma B. Now see friends, what is Cartesian product? For any two sets, Cartesian product of two sets is denoted as A cross B, and A cross B is equals to set of all ordered pairs of A comma B. Friends, I am talking about ordered pairs. Set of all ordered pairs of A comma B such that for all A belongs to capital A and B belongs to capital B. So in this context, we can write A cross B as all the possible ordered pairs, friends. All we have to write. So 1 comma A, 1 comma B, 2 comma A, 2 comma B, 3 comma A, 3 comma B. These are the 6 elements in the Cartesian product of two sets. Okay. Now from this we can say one thing, friends. If n of A is equals to some m, n of B is equals to some n, then number of elements in A cross B, that is n of A cross B is equals to m into n, or we say mn, m into n or mn. If there are m elements in set A, n elements in set B, then number of elements in A cross B will be mn. Next, void relation, universal relation, identity relation. Before we start this, let's discuss what is relation. Capital R is said to be a relation from capital A to B if R is subset of A cross B, friends. If R is subset of A cross B, then R is called as a relation defined from A to B. That's it. Very simple. R is said to be a relation from A to B if R is subset of A cross B. That's it. Now, for a given set, suppose if there is a set A has n elements. Number of subsets of A will be 2 power n. So, in the same way, each subset of A cross B, if it is a relation from A to B, in A cross B already we have mn elements. Just now we have seen. In A cross B we have m into n, mn elements. So, total number of subsets of A cross B is 2 power mn. Therefore, there exists 2 power mn relations from A to B. So, if n of A is equals to m, if n of B is equals to n, then total number of relations from A to B is 2 power mn. Total number of relations, if n of A is equals to m, n of B is equals to n, total number of relations from capital A to B is 2 power mn. And next, void relation. Void relation means an empty relation, a relation which consists no element. Let's say R is a relation defined from n to n, natural numbers to natural numbers. Okay. Now R is equals to set of all ordered pairs of x comma y such that x plus y is less than 1. X plus y is less than 1. Can we get any ordered pair such that x belongs to natural number, y, x comma y both belongs to natural numbers? Do we have any ordered pair such that x plus y less than 1? No. Such a relation is said to be an empty relation or void relation. Next, universal relation means A cross R is, if R is a relation from A to B, universal relation means A cross B only. A cross B only. So, if R is a relation, if R is a relation from n to n, suppose, let's say n to n, how do we write universal relation? R is equals to set of ordered pairs of x comma y such that, same friends, x plus y greater than 1. If x plus y is greater than 1, this is going to be true for all x belongs to capital N and y belongs to capital N. So, we will be considering all the ordered pairs, all the possible ordered pairs of x comma y such that x comma y belongs to capital N. Next, identity relation. Identity relation means, suppose set A is equals to some 1, 2, 3. Now, from identity, even all these relations, we will be defining only binary relations. What is binary relation? Binary relation means instead of relating from one set to the other set, we are going to relate from one set to the same set. Relation from A to A, B to B, N to N, K to K. Okay? Now, all these we will be discussing only binary relations, friends. Only this we have in the syllabus. Now, coming to binary relations, in that identity relation. Identity relation means if capital R is a relation from A to A, R is a relation defined from A to A, it is said to be identity relation only when each element of A is related to itself only. Is related to itself only. Friends, this only makes everything. Only is important. Clear? Because each element of A is related to itself. If you stop there, you are also giving a chance that each element is related to itself. Apart from that, it can also relate with another. No. what we are saying, we are restricting to each element of A is related to itself only. That means 1 should relate to only 1, 2 should relate to only 2, 3 should relate to only 3. So identity relation on A is denoted as IA, friends. And IA consists only exactly 3 ordered pairs: 1, 1, 2, 2, 3, 3. 1, 1, 2, 2, 3, 3. This is the only, if n of A is 3, then n of I, there will be only 3 elements in identity relation only. Okay? Each element of A is related to itself only. Reflexive relations. Now we have 3 most important types of relations. They are reflexive, symmetric, transitive. What is reflexive? Capital R, a relation from A to A is said to be reflexive, if it contains A comma A for all A belongs to capital A. Do understand the difference between reflexive and identity, friends. In identity, what we said, each element is related to itself only. That means A should be related to A only. Each element of A is related to itself only. But in reflexive, what we are saying, each element is related to itself, but we are not stating only. Clear? Is that okay? That means 1, 1, 2, 2, 3, 3 should be compulsory part of R to be reflexive. Now apart from that, whether we have some other ordered pairs or not, we won't care. Whether they can be, even if they are, it is reflexive. Even if they are not, it is reflexive. Clear? I mean to say, suppose same set we take, friends. Set A is 1, 2, 3. Now I am taking a relation R1 is equals to 1, 1, 2, 2. That's it. Now is it an identity relation? No, because 3, 3 is missing. Is it a reflexive relation? No again. We are not having all A comma A for all A belongs to capital A. We have 1, 2, 3 belongs to capital A. That means 1, 1, 2, 2, 3, 3 should be there. These 3 should be there compulsory. So R1 is not reflexive. Now to make it reflexive, suppose if I have 3, 3 and 3, 1 also, friends. Now see, is it an identity relation? 1, 1 we have, 2, 2 we have, 3, 3. Along with that 3, 1 also we have. So it is not identity. In identity only 1, 1, 2, 2, 3, 3 should be there. But, so it is not identity. Next, is it a reflexive relation? Yes, it is a reflexive relation. Why? Because 1, 1 we need, 2, 2 we need, 3, 3 we need. Thus, if these 3 are part of the relation, then it is reflexive. Apart from that, whether a particular ordered pair exists or does not exist, we won't care. Now apart from that, we also have 3, 1. Who cares about it? So it is a reflexive relation. Is a reflexive. Next, symmetric. Symmetric means a relation capital R defined from A to A is said to be symmetric if A comma B belongs to R implies B comma A belongs to R. That means when A comma B exists, B comma A should exist. If it does not exist, then it is not symmetric. If a relation is not symmetric, then it is antisymmetric. Okay? If a relation is not symmetric, then it is antisymmetric relation. Now, one thing. Let's see this, friends. This definition is only taken as rejection purpose. What do you mean by rejection purpose? If A comma B exists, then only you will be checking the existence of B comma A. If A comma B exists, then only you will be checking the existence of B comma A. So if A comma B exists, in that case, if B comma A exists, it is symmetric. And in that case, if B comma A does not exist, only in that case we say that it is not symmetric, which is antisymmetric. Example C, friends. Let's say some R is equals to 1, 1. is this relation a symmetric relation or not? First, what we see, we check for A comma B. Do we have any A comma B in this? No. So when we doesn't have A comma B, what is the necessity of checking B comma A? Not at all. That means it is symmetric. It is symmetric. Second case, suppose R2 is equals to 1, 1, 1, 2. In this case, 1, 1, it's not A comma B. 1 comma 2. Yes, A comma B exists. So when A comma B exists, check for B comma A. Do we have 2 comma 1 in that? No. Hence it is not symmetric. So we say a relation is not symmetric or anti-symmetric only in one case. What is that case? When you found A comma B, but in that case if you can't find B comma A, then such relation is called as anti-symmetric. So this is anti-symmetric. To make it symmetric, we just add 2 comma 1. Hence it will be symmetric now. Next, transitive relation. Same story, friends. This definition is also a rejection purpose only. That is, if A comma B belongs to R and B comma C belongs to R, in this case, check the existence of A comma C. Then we say it is transitive. If it does not, when both presents and in that case A comma C does not exist, that is not transitive. Clear? Next, equivalence relation. Equivalence relation means if a relation is reflexive, symmetric and transitive, then such relation is called as equivalence relation. Equivalence relation. Now apart from that, we also have trivial relations, friends. Trivial relation means a relation from A to B is said to be trivial only when if it is either empty relation or we say universal relation. These two relations are called trivial relations. Next, different types of relations that we have are partial order relation. Partial order relation. Partial order relation. Kindly make a note of this. This is very important. Partial order means a relation R from A to B is said to be partial order if it is reflexive, anti-symmetric. Here it is symmetric, no? Here it is anti-symmetric and transitive. So if a relation is all the three, then such a relation is called as partial order relation. Next, number of relations. Friends, this page is going to be very important. We'll just start writing. If there are n elements in set A, friends, if n of A is equals to n, starts with number of relations from A to A is equals to 2 power n square. We know it. Number 2, number of reflexive relations. Number of reflexive relations from A to A only. 2 raised to n square minus n. Number of symmetric relations. 2 power n into n plus 1 by 2. Number of reflexive and symmetric relations is equals to 2 power n into n minus 1 by 2. We don't have any formula to find number of transitive relations. Apart from that, we also have number of equivalence relations. Number of equivalence relation is equals to Bell number, we say. What is Bell number? We get it from Bell tree. Suppose if number of elements in A is 1, then we just we write 1. This is Bell tree, friends. If n equals to 2, then we start with 1, 2. So number of elements in 2, then we get 2 elements, 1 plus 1, 2. If n equals to 3, we have ended with 2, no? So 2 plus 1, 3, 3 plus 2, 5. We just add a number which is just above it. If n is 4, We ended with 5 now. So we start with 5. 5 plus 2, 7. 7 plus 3, 10. 10 plus 5, 15. So and so on. So this number is called as Bell numbers, we say friends. This number is called as Bell number. This Bell number is equals to number of equivalence relation. So if n is 1, 1 equivalence relation. n2, 2 equivalence relations. 3, 5 equivalence relations. 4, 15 equivalence relations. We go on. If you take n equals to 5, then we draw the bell tree and get it. So with that we are done with relations also. Next, the last topic in this session is functions. Now coming to, first we'll see definition of a function. Definition of a function. See friends, we have already seen a relation. Now definition of a function means a relation from capital A to B is said to be a function, if each element of A has exactly one image in B. If each element of A has exactly one image in B. Let's use Venn diagram, arrow diagram. Each element of A has exactly one image means, friends, suppose 1 map with A, 2 is mapping with 3. Now this 2 except B, it should not map with any other. 3 with a D. This is a function from A to B. F maps from A to B is a function only when each element of A has exactly one image in B. Now see this friends, if F is a function from A to B, we call it as F of 1 is equals to A. F of 1 equals to A and F of 2 is equals to B. When we write F of 1 is equals to A is image of 1. This A is image of 1 and 1 is pre-image of A. A is image of 1, 1 is pre-image of A. B is image of 2, 2 is pre-image of B. D is image of 3, 3 is pre-image of D. E is image of 4, 4 is pre-image of E. Next, vertical line test. For a given graph, how do we check whether it is a function or not? Suppose if we have a function, we have a graph. Now what we do is, we draw vertical lines friends. If this vertical line intersects exactly at one point, then it is a function. If it intersects more than one point, it is not a function. Let's see. Suppose we have a function. We have a graph like this. Then draw vertical lines. See, this vertical line intersecting more than 2 points, then this is not a function. Not a function. It is a function. Next, functions generally that we commonly come across are modulus functions, which we know y is equals to mod x, logarithm function y is equals to log x to some base a, exponential functions y is equals to a power x, greatest integer functions, step function, GIF means step function. Next, fractional part function. Next, trigonometric functions, sine, cos, tan, secant, cosecant, cotangent. Inverse trigonometric functions, sine inverse, cos inverse, tan inverse, secant inverse, cosecant inverse, cot inverse. Algebraic functions, generally algebraic functions means x plus 1 something and all this comes under x plus algebraic functions only. Rational functions means any function which is of the form of some f of x by g of x. Now friends, you should know the domain and ranges of all these functions friends. Domain and ranges of all these functions. Domain and range of trigonometric functions we have seen. Domain and range of inverse trigonometric functions we have seen. Generally domain of algebraic functions will be set of real numbers. Range will also be set of real numbers. It varies actually. Next, domain of a function. Domain, what do you mean by domain of a function? Domain of a function means the set of values of x where f of x is defined. Simple. all the set of values of x where f of x is defined. So example I take, f of x is equals to square root of 9 minus x square. This function is a square root function. Square root function is defined only when inside the square root it should always be greater than or equals to 0. So x multiply with a negative, x square minus 9 less than or equals to 0. X plus 3 into x minus 3 less than or equals to 0. That means x belongs to closed minus 3 to 3. So only for x belongs to closed minus 3 to 3, the square root of something inside root it will be positive or even equals to 0. That means if x takes only from minus 3 to plus 3, this f of x is defined. This is going to be the domain of the given function. Okay? In that way we can find the domain of all the different functions, friends. Logarithm function we have already discussed in the session. As this is a recap session, I'm just summarizing it. Okay? Next, range of a function. Generally range means, now for the given domain, all the collection of outputs, the set of outputs will be the range of the given function. There are different ways of finding the range, friends. First, by using common sense. I know you'll be getting smile the moment you look at this. Common sense means, generally see this, friends. We have a function f of x is equals to mod of x plus 1 plus 10. Mod of x plus 1 plus 10. Yeah. Such functions, what is the range of this? You know clearly mod of anything will always be greater than or equals to 0. So this will be greater than or equals to 0. For that 10 is added, man. So for sure this is going to be always greater than or equals to plus 10. Clear? This will be always greater than or equals to plus 10 now. Now next, in the same way, suppose if we have another function, f of x is equals to sin x plus 3. We know the range of sin x. Sin x will always be from minus 1 to plus 1. Minus 1 less than or equals to sin x less than or equals to 1. We just add 3, minus 1 plus 3 less than or equals to sin x plus 3 less than or equals to 1 plus 3 is 4. So 2 less than or equals to sin x plus 3 is our f of x less than or equals to 4. See, now the range of f of x is from 2 to 4. Such cases we do it by using common sense. Next, expressing x in terms of y. Suppose we have a function y is equals to x plus 1 divided by 2x minus 1. To get the range, what we do is, what is domain? Generally denominator cannot be equals to 0, that is domain. So domain of this function is 2x minus 1 not equals to 0, x not equals to 1 by 2. So x belongs to r minus 1 by 2 is our domain, friends. Now to get range, we express x in terms of y. Cross multiply karo. 2xy minus y is equals to x plus 1. So all the x terms on one side. 2xy minus x is equals to y plus 1. X common, 2y minus 1 is equals to y plus 1. X equals to y plus 1 divided by 2y minus 1. Now find the domain for y. That means 2y minus 1 not equals to 0, y not equals to 1 by 2. That means range, y values means set of values of output. So r minus 1 by 2 is our range. Domain is same and range is also same. So one method of finding the range is expressing x in terms of y. Next, by using AM/GM HM inequality. AM/GM HM inequality. AM of given two numbers. Suppose let A comma B are any two positive numbers. Arithmetic mean of these two will be A plus B by 2. Whereas geometric mean root A. Arithmetic mean will always be greater than or equals to geometric mean. This is for any given numbers. Okay, by using this also we will be getting maximum value of some expression, minimum value of some expression. Clear? Next, differentiation. We did it in differential calculus. Okay, by using differentiation, what we do? For a given function y is equals to f of x, we differentiate it f dash x. Suppose they are asking us to find the range of the function f of x in some closed a comma b. If they say find the range of the function f of x in some closed a comma b, we find f dash x, and if f dash x is greater than or equals to 0 in this region, if f dash x is greater than or equals to 0 in this region, that means f of x is increasing, man. F of x is increasing function. If it is increasing, that means that for the lesser input you get lesser value, for the higher input you get more value. So range will be clearly from f of a to f of b. We find f dash x. We find f dash x. If f dash x is found to be positive in the given interval, then it is increasing in that interval. When it is increasing in that interval, range will be f of a to f of b. In the same way, if f dash x is less than or equals to 0, that means decreasing in the given interval, then range will be from f of b to f of a. From f of b to f of a. Next, trigonometric range. In this, one of the most important common expression that I would like to give you. F of x is equals to a sin x plus b cos x plus c. Range of this trigonometric function, which we use it many number of times. Minimum value of this is c minus of square root a square plus b square, and maximum value of this is c plus of square root of a square plus b square. Friends, I remember majority of the times we have discussed this proof in the classroom. Okay. So minimum is this, maximum is this. They ask range from minimum to maximum. Closed brackets from minimum to maximum. Range. Next, in functions, the different types of, most two important different types of functions that we have are 1, 1 and onto. First we go with 1, 1 and many to 1. Simple definition of 1, 1 is, if f is a function from a to b, friends, no two elements of a should have the same image in b. That's it. No two elements of a should have the same image in b. That's it. Clear? That means we can also say that if f maps from a to b is said to be 1, 1 function, for all x1 comma x2 belongs to a, for all x1 comma x2 belongs to a, such that f of x1, if f of x1 is equals to f of x2, implies x1 is equals to x2 only. That means if two are having same image, that means two are same itself. If f of a, I mean input a, an element a is having an image something some x, element b is also having the same image x, this should be 1, 1 means a and b should be the same element. That's it. A and b should be the same element. A should be equals to b. Then only we say it is 1, 1 function. Now many to 1 means if a function is not 1, 1, then it is many to 1. Clear? Next, number of 1, 1 function. This is something which is important, friends. First case, number of 1, 1 functions from a to b, if n of a is equals to m, n of b is equals to n. N of a is equals to m, n of b is equals to, that means there are m elements in set A and f is a function mapping from a to b. Then number of 1, 1 functions, 3 cases, friends. I am splitting it as 3 cases. M greater than n, m equals to n, m less than n. Now in these 3 cases, if m is greater than n, there exists no 1, 1 function. If m equals to n, then n factorial or m factorial, both will be same. If m is less than n, number of 1, 1 functions will be npm. npm means number of permutations of m objects taken out of n objects. Next, this is regarding number of 1, 1 functions. Next, we also do horizontal line test. If any graph is given, by using horizontal line test, we can analyze whether it is 1, 1 function or not. See, just by using horizontal, we draw horizontal lines. If this horizontal line intersects at more than one point, then it is not 1, 1 function. Next, onto function. Clearly onto function means, in simple words, a function f maps from A to B is said to be onto if range is equals to codomain. That's it. If range of the function is equals to its codomain, then it is onto function. So range should be equals to codomain ma. That means f maps from A to B is onto if for all y belongs to B, there exists x belongs to A such that f of x is equals to y. For all y belongs to B, there should exist x belongs to A such that f of x is equals to y. Then we say such function is called as onto function. If a function is not onto, then it is into. Next, number of onto functions. Same story. Function f is mapping from A to B such that n of A is equals to m, n of B is equals to n. Then number of onto functions in three cases: m greater than n, m equals to n, m less than n. If m is greater than n, friends, number of onto function, actually we do it by using the principle of inclusion and exclusion. I proved it in class. I am writing just the formula. M greater than n, number of onto functions will be, total number of functions is n power m minus nc1 into n minus 1 power m plus nc2 into n minus 2 power m minus nc3 into n minus 3 power m and so on, where m is number of elements in A and n is number of elements in B. If m equals to n, it will be n factorial. If m is less than n, it will be 0 only. And one more thing, friends, if n of A is m and n of B is n, number of functions from A to B, number of functions from A to B is n raised to m. Number of 1, 1 we have seen, onto we have seen. Next, into means if a function is not into, then it is onto only. So with that, we are done with these 1, 1 and into functions, 1, 1 onto. Next, many to 1 into functions also. Next, even and odd functions. Even and odd functions are very simple, friends. A function f of x is said to be even if f of minus x is equals to f of x. Such function is even function. Best example is cos x. In trigonometry function, we have cos x because cos of minus theta is cos theta. Next, a function is said to be odd if f of minus x is equals to minus f of x. Best example, sin x. Even function will always be symmetric with respect to y-axis and odd function will always be symmetric with respect to origin. Clear? Next, periodic function. A function f of x is said to be periodic if there exists a smallest positive number t, such that f of x plus t is equals to f of x and the smallest possible value of t is said to be period, of the given function. Period of sin x, cos x, cosecant x, secant x, cosecant x, all these periods are 2 pi. Period of tan x, cot x are pi. Okay. Next, period of mod sin x, mod cos x, mod secant x, mod cosecant x, mod tan x, all if we have modulus. Period of mod f of x for all f of x is equals to sin, cos, tan, cot, secant, cosecant. Period is pi itself. Okay. Apart from that, we also have some more. If f of x period is some t, then period of f of ax plus b will be t by mod a, friends. This is very important. That means suppose sin x period is 2 pi, we know. Sin of 3x plus 10 period will be 2 pi by 3. Okay, just divide with the coefficient. So this is regarding periodic functions. Next, composite functions. Composite functions means generally we have f circle g, g circle f. F circle g means f of g of x. G circle f of x means g of f of x. This we call it as composite functions, friends. That means f is a function mapping from a to b. G is a function mapping from b to c. G is a function mapping from b to c. So now G circle f is a function mapping from a to c now. Okay, simple words. G circle f is a function mapping from a to c. This is what we say composite function. Next, inverse of a function. Inverse of a function mean same like finding the range, friends. Almost it is very equals to finding the range itself. And in almost proving onto, to prove a function as onto, what we do, we equate range, we find the range and equate it to codomain. No? We show that it is equals to codomain. No? Finding range part is nothing but finding inverse itself. Okay. Inverse exists only when the function is bijective function. First thing is, inverse of a function f maps from a to b exists only if it is bijective. What do you mean by bijective? Bijective means if a function is both 1 1 and onto, then it is bijective. So imagine that f maps from a to b is bijective, friends. F maps from a to b is bijective. Then there exists a function g mapping from b to a, g mapping from b to a such that g mapping from b to a such that abc 1 2 3 a21 b22 c23. This function is called as inverse of the given function. F inverse is equals to g. And if f comma g are inverse to each other, friends, f circle g of x is equals to x, or g circle f of x is also equals to x. These two are the most important conditions. Next, one more thing. A function f maps from a to b is said to be bijective only if it is bijective, then n of a will be equals to n of b. N of a is equals to n of b, and number of bijective functions will always be equals to n factorial. Number of bijective functions. Number of bijective functions is n factorial or m factorial, because n of a is equals to n of b, no? So that's it, friends. This is regarding complete functions now. So friends, in this session, we are done with sets, relations, functions. I have covered each and everything, friends. Each and every point related to mains I have covered. Even related to advanced also I have covered. So I request to watch this video carefully and note down all the important points. If you are clear with all the each and every concepts from this particular video, you are clear with complete concepts from all these three topics. Okay, wish you all the very best. See you in the next session. Till then, take care everyone. All the best.